Okay, so today I had a couple things I wanted to go over with rotational kinematics. I know you guys had some questions on those problems. So I thought let's start out by really going back over our theta, omega, and alpha and what those really are, okay? So a theta is an angular position. It's just basically where you are at. It's kind of like your x equivalent, but for rotational motion. So if we go take a look at the wheel again, right? If you've got a dot on the wheel, let me see if I can get zoomed in here so you can see a little better. Yeah. Okay, so there's my dot. If I want to know where it is right now, well, the way I have to describe that is in terms of theta, right? So I have to describe it in terms of like basically how many radians it's gone through, okay? So from here to there, it's gone pi over 2 radians, okay? A little bit farther, it's gone pi radians, a little bit more, 3 pi over 2, and then back to 2 pi radians or a full cycle, right? One full circle. So if I want to figure out basically where I'm at, I have to use theta. I have to figure out how many radians I've gone through, okay? Rotational or angular acceleration, angular velocity, right? Those things have to do with basically how fast the wheel is going around. So if I want to go faster, again, I'll have some kind of a set speed like this, and you can kind of see the dot a little bit on there. You can kind of mark how many radians it's gone through per second. Angular acceleration, if I'm going at some speed and I speed it up, then I've accelerated and I'm going through more and more and more radians per second. So, but let's take a look at how that relates back to linear stuff real quick. Okay, so if I want to get, that's a position, isn't it? Sure, at that dot, I've gone through so many radians to get up to here. But I've also covered an arc length. I've actually covered that length distance. So if I want to know what that arc length actually is, I can do that, and it's pretty easy to figure out. So what you need is figure out how many radians you've gone through, right? And it turns out if you want to know your x position, and really I shouldn't call it x, I should call it my arc length, which usually they call s, okay? I'm still going to call it x because it's just a distance we've covered, right? So if I want to know the distance that's been covered by that dot as it spun around on the wheel, what I need to know is basically how many radians I've gone through and how far out from the center it was. So number of radians you've gone through times your radius will actually get you your arc length or your distance covered by that dot or wherever you're at on the wheel. Okay? So there's kind of an easy relationship. Anytime you want to get to a linear variable, okay, the linear version of it, all you have to do is take the rotational version and multiply it by the radius. And that's it. You'll actually get straight back to your linear variable. So let's check this out. Angular velocity. Okay, first off, I had a question. Why does it say angular velocity instead of angular speed, vice versa? Like, is there a difference? Yes, there is. Take your right hand, okay? Your right hand, you're going to take and curl it around in the direction that the wheel goes, okay? So if the wheel is going this way, I would curl my fingers in this direction. You see which direction my thumb is pointing? It's pointing towards you, right? So that means I have, because it's going counterclockwise, right? I'm getting a positive angular velocity out of it. If I were to go the other direction, my right hand rule would say I curl my fingers in the direction the wheel is going, and you'll see my thumb will actually point away from you into the board, right? So that would be a negative direction for angular velocity. So just to clear that up, okay, angular velocity, if you're going this way, it's positive. If you're going that way, it is negative. Okay, that's generally the convention that people follow, right hand rule. Okay. What if I wanted to get my velocity from this? Well, again, I'd have to know, if I want to know my linear velocity, I'd have to know how fast around I'm going, and I need to know distance away from the center. Okay. An angular acceleration. So angular acceleration, what that is, or tangential acceleration, if I'm going around like this, the tangential acceleration, all of these variables are the thing that happens at that tangent to that point, right? It's going to be on the outside of a circle, or if it's some distance in, it's not a full radius length away, right? Well, it's still going to make a circular change here, right? You're still going to have a tangential velocity, right? Tangential velocity, tangential position, or really an arc length, right? Or a tangential acceleration, how fast am I speeding up on that edge, okay? So if I want to know my A tangential, okay, on the outside of the circle, what's my acceleration? Well, same thing applies. If I'm speeding up how fast I'm going around, right, faster and faster, I have an alpha, okay? I have an angular acceleration. And just like this, it can have a positive, right, curling around this way, counterclockwise, positive angular acceleration, or it could be a negative, right? So on this one, if I want to find my tangential velocity, I simply multiply that angular acceleration that it's experiencing and how far out it is from the center point, right? Its radius. And that right there will get you to your straight line, your linear variable from your rotational, okay? So let's go ahead and solve a couple problems. I know you guys had a couple questions on number 2, and then on to number 6. It had an issue with the time on it. I think I'm actually going to leave, I'll work out number 6 here too. And so number 2 basically was asking about, you have 2 people, 2 kids, right, on a merry-go-round. One's out at the edge and one's on the interior. I think that's how it went. Marilyn and Sheila there. Okay, so yeah, number 2, I had Marilyn was on the outside, Sheila was on the inside. Okay, and it wants to know, okay, one is halfway, so there's the center point, okay, so it's all rotating around that center, okay. Everything's going around the center of the merry-go-round, which is important. They're not rotating about this point, right? It makes a difference, okay. And then this radius here is 1/2 of r, and this one here is just r out to Maryland, okay. So it wants to know, what is the relationship between the centripetal acceleration and the 2 sisters? Well, centripetal acceleration is going to be basically the centripetal acceleration, if you remember, is v squared over r, or omega squared times r, okay? So you can imagine, as you're farther out on this wheel, right, you've got a higher v, even though your angular velocity stays the same. So as your r increases, right, even if you've got the same omega out here, everybody's traveling the same number of radians per second, the farther you go out, you're covering more distance, so you've got a higher centripetal acceleration. Closer you are to the center, the lower your centripetal acceleration, okay? So if you're closer to the center, you're actually feeling less of a push, right, in or out, centripetal or centrifugal, right? If you're on the outside, you're feeling more.